Our first speaker is CJ Lai from Academia Sinica, and he will be speaking on quantum Wreath products.
Yeah, thank you. It's my honor to be here. So today I'll be talking about some things we've been thinking about and joined with Dan and some other collaborators. It all started with this combination when I was still a postdoc at UGA. And here, this is a former student of UGA, Ziqing. He's now in SUSTEC. And in the picture, we were pretending discussing some math. Okay, so the question that we were thinking about is a problem raised by Ginzburg, Guay, Opdam, and Rouquier for the type A Hecke algebra. So in short, this is about the study of red theory of those Hecke algebra for complex reflection groups and some of the related algebras we will show up later. And one of the essential steps is to study this very special subalgebra of a type A Hecke algebra of an even rank so that you can impose extra internal symmetry. So this is something we call the Hu algebra. So this is because it first appeared in a Morita equivalent theorem due to Hu between Hecke algebra of type D and some Hecke-like algebra of type A. I'll come back to this later. And what we discovered, and this is the slogan for today, is this algebra, Hu algebra, is really something we think that can be called the Hecke algebra for the Wreath product between symmetric groups. So know that these symmetric groups are not even toxic groups. So we claim we can extend the notion of Hecke algebra from complex reflection group to a larger family because of some, I would say, supporting evidence. And then when we did this, we find it is useful to use a new notion that we call the quantum Wreath product that can treat some of these Hecke-like algebras in a more uniform way. And it happens to include all these algebras as special cases. I'll come back to the list later, of course. Okay, so let me start with what we call the GDOR problem due to these people. So quick reminder, as I said, Hecke algebra was first introduced for Weyl groups and then later extended over the notion of complex reflection groups. And the standard way to study representation theory of the Hecke algebra is to use this highest weight cover, which means a nice functor that goes from a highest weight category to the module category of the Hecke algebra. And these are highest weight categories are due to Klein partial Scott. And so the goal is, how do we construct nice highest weight covers for Hecke algebra over complex reflection groups? And one way is a theorem due to GGOR. They prove that you can construct such a highest weight cover by considering the corresponding rational Schur algebra, which is a doubly degenerate version of the affine, double affine Hecke algebra. And then they show that, okay, this is a highest weight cover, but it may not be the nicest, which means this is a one faithful cover. The terminology is due to Rouquier. And at least for type A, this is later proved by Rouquier that the KZ functor is indeed the nicest highest weight cover under some assumption on the parameters. And then they have this nice diagram, commutative diagram. So you have on one side a category O for the rational Schur algebra. You have this KZ functor defined through monodromy and localization functors, etc. But on the other hand, it is also known that the Q-Schur algebra, the module category, provides a one cover of the Hecke algebra, and hence you have this diagram. The top row the top row is equivalence as highest weight categories, and then which means you can identify this rather complicated KZ functor with the much more explicit Schur functor, which just take a module headed by an idempotence. Then beyond type A, there has something to be done. So our question is then, can we construct similar finite dimensional algebra, maybe the Schur algebra, and then construct the nicest one cover, the Schur functor that you can get to go from this module category of a finite dimensional algebra to the module category of the Hecke algebra, so that this can identify the KZ functor produced by GGOR. So for type D, Rouquier made an essential work by constructing establishing a theory of this one cover. And then we then prove that we can combine Rouquier's theory and some other ideas coming from quantum groups or co-ideal Schur algebras. And then we can construct such a Schur functor using, inspired by the Morita equivalence theorem between Hecke algebra of type B and some Hecke algebra of type A, I mean, maximal parabolic subalgebras. And then recently, there's a different approach due to Ben Webster and his student. I think it's on arXiv this year. Then we are trying to move on from type B to the complex reflection group, PPD. This is the index P subgroup of a generalized symmetric group. In particular, this is, I think, possible because there is Morita equivalent theorem similar to the flavor of type B. So like for type D, it is first showed up in Hu Jing's paper, and then Hu Jing and Andrew Mathas, I think, generalized this to a more general type for complex reflection group. But for today, we'll be only focusing on the type D case. And you can see that when the rank D is even, there's an extra subalgebra that's like very special compared to the type B situation. Okay, so again, our slogan, this algebra, the Hu algebra, should really be thought as a quantization of the subgroup SM with S2 inside a larger symmetric group. So just to give you a crash course on Wreath product, whenever you define such a thing, you take a direct copy of your possibly infinite group G, and then you take a semi-direct product in which you identify a typical element this way. So you can move like element in the symmetric group to the other side by also place permutation these tuples. And the well-known example is if you take G to be the cyclic group of order 2, this produces the Weyl group of type B on the nodes. So I like this visualization of a permutation of a height 2 rooted tree. So the type B node, what it does is just to permute these two nodes of your subtree, or if you like permutation of integers, this is the permutation between -1 and 1. And then the type A generators permute these subtrees. So this forms a permutation subgroup from -D to D. And then you can easily show that this is the Weyl group of type B. The other extreme case, I think, is less familiar. You want to take two symmetric group on M letters, and you only have one extra generator that swaps the whole thing. Or in other words, you have a thickened crossing of thickness N that was in, say, John's talk already. Of course, in Wei-Chung's talk already. And then when we look at this group, SN Wreath S2, we want to quantize this guy, but a naive quantization will not work. So this is because we want a quantization, an algebra that has dimension equals to the order of this group. So if you just take the naive, say, standard basis element corresponding to this Weyl group element, you won't get what you want. Say, if you take the case M equals to 2, your extra generator is a thick crossing of length 4. This is an evolutive element. But the naive quantization, T2 times T3, T1, T2, has a very complicated power When you square it, you produce something that's not in the group, and hence the corresponding dimension will be greater than the order of Sn Wreath S2. And it may seem like hopeless to find such a subalgebra, but who made a good observation and it made it actually possible. So Chun-Ju started with this type B construction. So you have a type B Hecke algebra of unequal parameters. The type B relation is actually degenerate, and you have a regular type A relation. And then you can consider such element. This is a product of UC-Smurfit elements. And then there's a rather complicated construction. He proved that there's a unique element that sits inside the type A part, satisfying some equations I don't want to go over. And then he showed that if you square this, this is a unique element in the center of the maximal parabolic subalgebra, such that something else holds. So let's pretend we don't have these two lines. I think I'll give you another property for this extra generator. So I want to now identify the maximal parabolic subalgebra with just the twofold tensor of a type A Hecke algebra. Then this special element is also an intertwiner or teleporter in, like, don't run this wording. And by that, I mean, if you put this on one side of any element in your tensor algebra, when you swap the two tensor factors, and the extra element goes to the other side. So this is diagrammatically exactly what you see as a teleporter in the previous pictures. So our first result is we have actually a explicit formula for this special generator HM. And I will start with some lower rank case to show you this is actually non-trivial. For n equals 1, this is still very manageable because you're asking to find one non-scalar element in the Hecke algebra S2 so that it squares to a scalar. So there's nothing much you can do, and you then realize you can take H1 to be just T1 plus its inverse. And when you square it, you get a square of quantum 2. For the next case, m equals to 2, you want to find something generated by T1, T2, T3, but that is not in the maximal parabolic subalgebra generated by T1 and T3. However, you want this guy to square into the center of this maximal parabolic subalgebra. This is a very elementary question. Like, you can ask this to a graduate student, and then the answer is, I think, surprisingly difficult. So for our formula, you want to take this thick crossing in every possible configuration, which means you want the strand to either go over or under the other strands. In terms of elements in the Hecke algebra, you want to take all the possible bar to some of these combinations. And then at the end, for some of these terms, you have to multiply by a UC-Smurfit element to make this guy square into the center of the maximal parabolic subalgebra. I think there is deep commutative going on here. When you square this, you get some coefficients that is rather mysterious. But if you have this central element act on some spec module, say trivial module, tensor trivial module, you actually get nice scalar multiple. So this is an observation, and we expect that this central element will act on these modules by a product of different types of quantum 2 squared. So if you have seen these numbers, please let me know. I'm very curious what this tells. Okay, so having this explicit formula, we can now study the algebra and its possible generalization when D is more than 2. So it's a fact that this Hu algebra has a following presentation. It can be generated by the tensor algebra I mentioned together with this extra generator. And the relation is, of course, that this H is an intertwiner, but the key observation is you have a relation that a quadratic relation, H squared, equals to some element in the maximum parabolic subalgebra. And I think the key observation is we really want to treat this as an analog of the usual Hecke quadratic relation. I mean, something like H squared equals to Q minus 1 H plus Q. This is an analog of that. And which means we need a more general theory accommodating this algebra with this generalized quadratic relation of the form. Those coefficients can be elements in the tensor algebra. They don't have to be in the ground field. So this is what we call a quantum Wreath product. So to justify why this is about Wreath product, we revisit the notion of Wreath product again. You have a base group you want to take a direct product with. You have you only need the braid relations, quadratic relations, and something determined uniquely by this local Wreath relation. And then for a quantum Wreath product, we mean this is now an associated algebra. You start with a base algebra. This can be non-commutative. So in our previous example, this B is a Hecke algebra of type A. And in some other cases, this is mostly a commutative algebra. You can take the ring of long polynomials or just the ring of polynomials. And then compared to the direct product, you do tensor product of this algebra. You keep the braid relation for these Hecke-like generators, and then you use the new quadratic relation in which coefficients can be elements in B tensor B. And then you allow this relation to quantize with a correction term. So sigma and rho here in general can be just endomorphisms. In practice, sigma is almost like the place permutation only, but it can be up to a scalar. And rho is very close to a de Majorque operator. With this relations, we are now defining an algebra generated by ODs subject to the local relations for I from 1 to n minus 1. That gives you the quantum Wreath product. So, we can now treat the whole algebra as a quantum Wreath product between between the Hecke algebra and the rank 2 case. You're using these local relations. And then this definition also encompasses the affine Hecke algebra. You can really treat this as the ring of Laurent polynomial Wreath Hn. You just need to write down the usual quadratic relation. And then it's not hard to show that the well-known Bernstein-Lussig relation can be determined uniquely from this local relation. And then the Araki-Koike algebra appears naturally as a cyclotomic quotient using the same parameters. And then you can also do the degenerate version by replacing this coefficient with 1. And then you use a degenerate quadratic relation, which also allows some degenerate version over some other Wreath product between groups due to Jinghui 1 and Weishan 1. And I'm saying these quantum Wreath product can also be thought as a quantization of the group algebra of these Wreath product. Some that are not even group. This is a monoid. And this actually go on. There are a bunch of names appearing in the literature, but I find it, I think it's more useful to understand what they are up to. For example, Savage and Rosso are interested in Heisenberg categorification. Such as Kleshchev, Robert Muth are studying these imaginary strata of KR algebras. Then Elias worked on KR and KR Webster algebras. Andrew Mathas and Katerina Stroppel are thinking of something that's the Rees algebra version of affine Hecke algebras. And then there's the Turner's conjecture by Evsip and Kleshchev. And those are the affine Yokonuma Hecke algebra, I think coming more from that theory and such. So I'm not saying our Wreath product algebra, like it's the solutions to everything. We just say, oh, we study Weyl algebra, we write down the most general formula, and it happens to contain these special cases, which suggests that there can be interaction between these different directions. I'm not saying our is the ultimate solution. And just to point out, there could be things that people want to think about. So since I don't have enough time, so I will just give an outline of what we have done. And you can see I have prepared some extras. So if you have questions, ask me and I will elaborate on that. So for the quantum Wreath product series, the first paper is about finding the necessary and sufficient condition to get a PBW basis of your quantum Wreath product. So there are conditions that has to be satisfied, and then we show that it's actually necessary. And then we talk about how do you get the Schur-Weyl duality for any such quantum Wreath product, as long as your base algebra is finite dimensional, a certain finite dimensional symmetric Frobenius algebra. And then this does means there's some rather mild technical assumption on the parameters. And then, as I said, our goal is to prove to answer the GGR problem for the complex reflection group of type GPPD. And then I think hopefully we can get to that point by the end of this year. And then we have some partial result of getting the one faithful highest cover from one to another. And then you may be wondering why I have list such a blank here, because when we're writing it, we have some like side project. For example, such a minute, and I think, for the first paper, we have this result for Schur-Weyl duality when the base algebra is finite dimensional. We can actually extend this further for certain infinite dimensional base algebra. So this is because this SA here appears in a previous work by Sasha Minette and Ruslan Maximo. They define such a thing called braided Schur algebra or curved Schur algebra, coming from a construction of a quote scheme. And then then I would say the key observation is the corresponding Hecke algebra is also a quantum Wreath product. So we can basically take the example, start with any smooth curve C, take its equivariant Borel-Moore homology, and then adjoin an extra variable X, and show that any algebra of this form can, we will have a uniform proof to the Schur-Weyl duality. And there's also a paper I, which is tangential to the real number. So we really hope that there can be a geometric representation theory for certain quantum Wreath product. And we started with the most naive one, which is the group algebra of the Wreath product between symmetric groups. And then the end result is we realized that this group's Wreath product between symmetric groups fit very nicely to a theory due to Iwahori. Iwahori first wrote a paper on generalized test system. It's about comparing the extended and non-extended affine Weyl groups. And then he wrote down some axioms that relax the condition of a test system. And we surprisingly find, okay, so this Wreath product between symmetric group happens to have a system that satisfies everything Iwahori wrote like 60 years ago. And then we will have a Gruhat decomposition as a consequence. And then you just need to find the right setup. So you'll get a Swinger correspondence for this Wreath product between symmetric groups, which I will call it like the geometric interpretation of the Clifford theory, which means in group representation theory, you know how to get to the irreducibles of your Wreath product from those of the irreducible of these groups separately. Okay. So some summary, we have a Hecke algebra that makes sense beyond complex reflection groups. this is a slightly larger family of groups. And then we, by that assumption, this is more like a wishful thinking, the Wreath product. We really want them to be the new affine Weyl group. Everything you can ask about affine Weyl group may have a chance to extend to the Wreath product case. And before you ask any question, can you do this for your quantum Wreath product? I will answer it first. Yes and no. The right question is, as long as you have a example, the right question is, what's the conditions on the parameters so your quantum Wreath product will have that property? So far we have proved, say, PBW basis, symmetric algebra structure, Schur duality under some assumptions, and something that can be done like easily, say, I shouldn't say easily, naively, the naive question is whether, say, cellularity, quasi-hereditary Clifford theory can hold when you have such base algebra with such properties, and then does it pass to this quantum Wreath product? Okay, so happy birthday then.
All right, thank you, CJ. It looks like he's ready for at least a dozen questions. So, questions? Yeah.
I have a question about this modified equivalence between the top D Hecke algebra and the
Yes.
full algebra with the top A. Does this equivalence require some polynomial invertible?
You have to assume that. So
that means the A and this whole algebra is defined under that assumption, right?
That's right.
Thank you.
To what extent can you deal with arbitrary characteristics?
We have not thought about that yet. So let's say, I mean, Steve Doty is interesting that he asked me the same question, but unfortunately I don't have an answer.
Oh, well, yeah.
Yeah, exercise for you.
Can you say something about your paper 1.5 and then paper I, essentially like the string of correspondence with the Wreath product?
Okay, so let's go to 1.5. Yes, so this is a quick like definition of the Schur algebra due to maximal and minette. So you can see that this it's almost of the form of a convolution algebra between partial flat variety, but this is a different version. So we look at the proof by Pouchon and think you can actually generalize this, and then you just need to show that you need to make some assumption so that this things on the right hand side, that's an analog of the complete flat convolution algebra is really a quantum Wreath product, and then you show that these local relations hold, and then they will include some affine zigzag algebra when you choose the smooth curves to be P1, and also it recovers the degenerate affine Hecke algebra. But there are some limitations. You can't do this for neo Hecke algebra. So there are something to say about this assumption state for this paper 1.5. And for the another one, this is basically what I go through. So the end result is you have a bijection between the irreducible for your Wreath product with some Borel more homology of some analog of string fiber taking its isotropic component, and then you can identify this with some of the index set you have coming from the Clifford theory. So this is a quick one. You can stare at it if you like.
Other questions? Okay, so the final talk of the day starts at 11:55, which is in 7 minutes. Thanks, CJ.